My name is Aditya. My partner Dhruv and I will be presenting a recent 2020 paper titled Adopt or Innovate: Understanding Technological Responses to Cap and Trade by Raphael Calel. The question examined in this paper is whether implementing cap and trade regulation schemes lead to firms adopting existing low-carbon technology or innovating new low-carbon technology. This question is an especially important one, as historically the imposition of said schemes has not led to an increase in firm expenditure on clean R&D projects, but rather the mere adoption of existing low-carbon technologies. While at first this may not seem problematic, when one looks at world pollution abatement goals, one can quickly realize that many of these goals will be impossible to reach without sufficient new innovative technology. For example, displayed is the Paris Climate Agreement. As one can see, the current path of emissions is quite drastically larger than the abatement goals. Hence, only through large innovative breakthroughs will we likely be able to achieve the goals outlined in this agreement. Thus, since most of the world's best innovations come from the private sector, it is vital to know whether regulations can successfully induce and encourage these innovations that may hold the key to reaching future pollution abatement goals. As such, firms responding to regulatory schemes through adoption of existing technology rather than innovation of new technologies presents problematic prospects. To put forth an example of this problem, the paper introduces the case of the American Acid Rain Program. Introduced in 1995, and the industry response. This was an American cap and trade program designed to reduce sulfur oxide pollution in the coal industry. Upon imposition of this environmental regulation, coal firms responded through adopting existing technology, namely scrubbers, an apparatus designed to clean the GHGs out of smoke prior to leaving the smokestacks. In conjunction with these scrubbers, already existing cleaner production processes were also employed. While one would expect the increased use of scrubbers to lead into innovation in the field over the coming years, either in the form of the invention of a more effective alternative or improvements on the existing design, the efficiency of newly invented scrubbers actually declined in comparison to the industry standard scrubbers that firms first adopted in response to this program. Furthermore, innovation in the field of sulfur oxide abatement technologies also regressed, as evidenced in the graph displayed, which shows that the patenting of new sulfur oxide abating technologies reduced after the imposition of the Acid Rain Program. Thus, introduction of this environmental regulation led to increased adoption of existing technologies and production processes, but a decrease in innovation in GHG abatement technology. Moreover, the same response pattern can also be observed in other industries in their response to similar environmental regulations. For example, when regulations were imposed on the use of CFCs, otherwise known as chlorofluorocarbons, in aerosol products. The focus of this paper is on the European Union Emissions Trading System, otherwise known as the EU ETS. This is a fairly newly imposed cap and trade scheme implemented on firms in the EU. The author tends to investigate whether firms and industries targeted by this new regulatory scheme will respond similarly to historical cases through increasing the adoption of existing technology and decreasing spending on new innovative GHG reduction solutions. To start the investigation, the paper introduces an economic modeling concept. The two graphs shown on screen illustrate the difference between what the author refers to as adoption and innovation. Adoption is defined as when a firm responds to environmental regulations through implementing existing technology, whereas innovation is when a firm responds to environmental regulation through creating new technology. In both graphs, the shaded area represents the savings gained from either adopting or innovating in response to the environmental regulations, rather than paying the emissions penalty. As one can see, adoption merely leads to moving along the marginal cost curve, which, because it is decreasing, leads to the firms having to pay even more for additional pollution abatement later if it becomes necessary. This is in contrast to innovation, which instead pivots the marginal cost curve inwards, decreasing the future marginal cost at all levels of emissions. Not accounted for in this graph, however, are the costs associated with both the processes of adoption and innovation. While one can expect great variation in the cost of both options across different industries and regulatory schemes, it is not unreasonable to conjecture that innovating new technologies likely poses a greater financial investment than adopting existing technologies. In addition to this, particularly unsuccessful R&D projects can represent a sunk cost if they do not yield any salvageable prospects. In the data analysis section of the paper examines both firms regulated under the EU ETS as a treatment group, and firms located in the EU but not regulated under the EU ETS as a control group. The researcher examines both groups' behavior to try and determine whether the treatment group begins to either innovate or adopt at a higher rate in response to the regulations, or if both groups behave the same. Furthermore, a matching design is implied to prevent extraneous variables such as the firm size from influencing behavior. Firms are matched such that only firms that are comparable in size and industry are compared. To measure whether a firm innovates or adopts, proxy variables are used. The proxy for adoption, the researcher uses emissions intensity. The researcher concludes that if a regulated firm reduces its emissions intensity quickly in response to regulation, then this could only be achieved through the adoption of existing technology. Thus, if immediately upon imposition of the regulations, a firm manages to reduce their emissions intensity, it can be implicitly concluded that they adopted. To proxy for innovation, the researcher examines how many patents the firm is filing, as well as examining specifically for patents pertaining to low-carbon technologies. Furthermore, R&D costs are also used in conjunction to proxy for innovation. While results will be looked at more into depth later in the presentation, from the graphs displayed, one can see that upon imposition of the EU ETS, there was a significant increase in low-carbon patents being filed. Moreover, since total patents did not follow the same trend, it's implied that the proportion of low-carbon patents relative to total patents increased as well. In doing their hypothesis tests, the researcher applies the following econometric model. In this model, delta n represents the difference in behavioral response between a group of matched treatment group and control group firms. Tau represents patents filed, which as I mentioned earlier is used as a proxy for innovation. T of n and C of n both represent the treatment firm outcome and control firm outcome respectively. The null hypothesis being tested for here is if the imposition of the EU ETS regulation has no predictive power over firm innovation, then delta n should be equal to 0 or a non-statistically significant deviation close to 0.
The results of the study can be divided into three parts. First, efficiency. Estimates suggest that EU ETS firms show an increase in CO2 intensity of 0.078 tons per 1,000 pounds of revenue, which equals to 20.7%. This does not mean that the EU ETS is the cause of the increase observed in CO2 intensities. Rather, it indicates that the EU ETS has not induced any adoption. Secondly, the EU ETS has evidently encouraged regulated firms to increase low-carbon patenting by 25%. If this effect is extrapolated for the 42 ETS firms that have been omitted, a total of 64 additional low-carbon patents have been introduced between 2005 and 2012. However, this does not account for any patents filed by unregulated firms as a result of the EU ETS, even if those innovations were meant to be sold to the regulated firms. Therefore, if that effect is significant, the results estimate a lower bound on EU ETS's effect on technological change. Lastly, the R&D spending. The EU ETS has encouraged significant low-carbon R&D spending among regulated firms. Including the omitted firms, the increase in low-carbon R&D spending is £11.6 million. The robustness of the findings must be analyzed further against a number of challenges. Alternative specifications. Alternative specifications show similar result. Slight increase in CO2 intensities, increase in low-carbon patenting, and R&D spending. This was discovered by comparing EU ETS's effects across 4-digit, difference in means, and difference in differences. Next up, selection. For this study, 42 EU ETS firms were omitted as they were much larger, more polluting, and more innovative. When these firms are accounted for, the results are larger with more statistical significance. There is also a selective exit bias. If less innovative firms are driven out by the EU ETS, the patenting and R&D spending would be inflated. However, this is unlikely as the least innovative firms were also less efficient than the average. Investments are declining among control firms, and the most innovative non-regulated firms would need to exit. Third, leakage. It would have been relatively less expensive for regulated firms to comply with the EU ETS by purchasing electricity instead of generating coal-burnt electricity. Thus, this could be considered a leakage and not a legitimate form of adoption. However, the control firms and the regulated firms exhibit similar pattern in their emissions from electricity purchased both before and after the EU ETS was introduced. Other policies can also be suspected to influence the findings of the study. For example, the government increased the R&D support during this period. This was, however, more heavily targeted towards small and medium-sized firms. Thus, it is unlikely that this would also explain the increase in low-carbon R&D spending by firms regulated by the EU ETS. Lastly, it can be argued that the EU ETS induced innovation by non-ETS firms. For example, another study implies that the spillover effect is as large as the direct effect, which would mean that the findings would need to be doubled. Hence, top innovators that are non-regulated polluters themselves but develop new technology can be compared with the ETS regulated firms. As the figure shows, after 2005, low carbon patenting increases for both groups with a little difference in their timing. Therefore, the estimates provide a lower bound on the EU ETS's effect on innovation, and the upper bound could be twice as much. A primary goal for carbon markets is to encourage firms to innovate and be efficient to achieve abatement. However, in retrospect, emissions have reduced under cap and trade policies mainly via adoption of existing abatement technologies, not primarily through innovation. For example, as Adi previously mentioned, the acid rain program, sulfur scrubbers for exhausts were available during the acid rain program. When the US government phased out leaded petroleum, pre-existing refining technologies were encouraged. However, the EU ETS faces a different set of preconditions. There is a lack of potential for low-cost strategies, for example, fuel switching. Current abatement technologies will be obsolete in the future to reach decarbonization goals. Therefore, it poses the firms an important question. Why invest in current abatement technologies? Firms much rather move resources from adoption to innovation. This explains that increased patenting and R&D expenditure are driving the development of new low-carbon technologies. These developments are expected to decline abatement costs in the future. Thus, it will be feasible to set more effective emission caps in the future in order to reduce the risk of climate change. It also must be noted that even for the world's largest cap and trade program, the data needed to learn about its effects is still unavailable. The effective sample sizes are often small. In order to improve the regulatory framework, the data collection practices also must be improved. Thank you for watching our presentation. We have two questions for our viewers. Question one, what do you think that regulators can do specifically in their policies to induce and encourage firms to innovate rather than adopt? Another question, how should the government allocate their R&D support to help firms innovate their low carbon technologies?